Thank you very much for your interest, for showing up today for our talk. We will talk about the virtual ECU on driving simulators with CarMaker. And let me talk to you about the agenda for today. I will start out with the goals of the research project MITAVI, which was the starting point for this collaboration. I will talk about our Audi driving simulator, what we use it for, and I will describe the technical concept, and then Franz Kramer will take over and talk to you about the results and the challenges in the development of this new tool chain, and we will then give an outlook and a short summary together. So, as I said, this collaboration was initiated by the MITAVI research project. Audi was asked if they wanted to contribute to this project with a goal to develop methods for the development of autonomous driving. And one very important aspect of this was how can humans be integrated in the development. And one possible solution to this are driving simulators. And as we operate the driving simulator, our department at Audi, the idea came to our mind that we could contribute to this project also. Now, the second part why we participated was the usage of SIL at Audi. We started approximately 2015 with the first virtualization of engine functions and diagnosis and small bits of software, basically, with open loop testing. Then improved to a powertrain SIL with a central processing unit and engine control, an entire engine control unit by Bosch, by the way, and also parallel and developed a chassis SIL with CarMaker for the simulation of the vehicle and the scenario, and Synopsys Silver for the simulation of the control units for the chassis software, like braking system, steering system, air spring control, and stuff like that. Now, in present, we are trying to bring these worlds together to get an entire driving system SIL containing the engines and the chassis functions all in one simulation environment. And as I said, we are using CarMaker for the dynamic simulation, and we distribute these models also to other brands like CARIAD and Volkswagen and Porsche. Also, Tier 1 suppliers use our simulation environment in a collaboration. So, with this background, I finally want to look at the driving simulator. Driving simulator has I don't know how long we have it. I think it was around 2012. It's a hexapod system that is used for mainly calibration of vehicle characteristics in early stages of the development. And in the past years, user experience studies for autonomous driving have become a very important use case because it is very much easier and cheaper to get test persons into a driving simulator and let them do various tasks of autonomous drivers than in real vehicles. And also a lot safer, of course. And so what we are trying to do there is we try to reuse a lot of the artifacts. We are using the very same CarMaker models as in our simulation on the driving simulator. And also we're using the same ResBus models for the vehicle functions as we do on our hardware in the loop and software in the loop test systems. So the goal, of course, is to substitute real vehicle testing in the early phases of development. However, nowadays, many of the assessment of characteristics depends on software functions. For example, it is not possible to rate a tire without the steering functions. So we were faced with a task to integrate the software into our simulation. And what we first did was to so this is how it looks now. We have the vehicle model, as I said, the CarMaker vehicle model, and we have our ResBus model, which is a big Simulink model, as probably many companies have. And this is very expensive to get all these SimECU functions to work properly. So yeah, we decided to attach our, in this case, electric power steering to the driving simulator with a vector hardware. We use a CAN bus for that, and it runs on a Windows PC. However, we're not really happy with this because first we need an extra hardware. There's a second PC standing around, and as it is a Windows machine, we don't meet true real-time requirements, which sometimes leads to stability problems in the simulation. Also, the performance is limited, and we can currently only simulate one VECU with this solution. And of course, the data exchange is also limited, so it would not be possible with this setup to simulate an ADAS function, for example. So our idea was, how can we integrate the VECU directly onto the real-time simulator of our driving simulator? So that was the goal of the MITAVI sub-project VECU on real-time systems. We wanted to enable the simulation of our chassis VECUs that we have in our office, SIL environment, on the driving simulator, on the real-time simulator, with no extra hardware. And also, it was important to us to reuse the existing VECU configurations because a lot of work has been done to get these running, and we didn't want to start a second branch of VECUs just for these real-time applications. And very important, as this project was conducted with project partners from other companies, one goal was to ensure the IP protection of the solution when we exchange the VECUs, for example, with a tier 1 supplier. So what we did was we decided to cooperate with Synopsys because they provide Silver, which we use for our office simulation. And I will hand over to Franz, who will talk to you about the solution that Synopsys came up with.
Right. Test. Okay. So let's talk about the why we want to actually integrate this. I mean, Andreas motivated parts of it, but in the end, the standard motivation for virtual ECU development applies, right? So it, with ever tighter time to market schedules and more complex systems, it makes sense to move to the, let's say, virtual world for software development, not just for model development and hardware simulations, let's say. And now, why do we want to integrate such a virtual ECU that could be used for virtual software development? Why do we even want to integrate this with a real-time system? Because in the end, let's say we want to alleviate the number of tests that have to be run on a hardware-in-the-loop simulator with virtual ECUs, right? But in the end, we expect two big impact areas. One is actually rest bus modeling. Because when you do rest bus modeling on hardware-in-the-loop systems, right, there are teams and teams worrying about model quality. So people are implementing functions in Simulink or any other modeling tool, or actually re-implementing functions that have been developed in embedded code in, let's say, the neighbor department, right? And this effort is something that we, let's say, by reusing virtual ECUs on the real-time system, would like to kind of cancel, right? We heard it in various other talks. We need to accelerate, we need to collaborate, and re-implementing functions in, I don't know, Simulink for a rest bus model for example, in a driving simulator or in a hardware in the loop setup is just not the way to go. So that's one area where we expect a big impact, because also, the more complex the systems get, the harder it is to even model them. So we've seen systems, let's say a big domain controller, if you need to model this, you need to cipher through, thousands of requirements that have gone into building, tens of software components to be actually integrated in the domain controller. And let's say this level of complexity is even something that you cannot model anymore, that you cannot re-implement anymore in a Simulink model, at least not with any feasible effort. So by integrating a virtual ECU, which contains real code, the real developed code for the real system, just in a virtualized environment, that, let's say, should significantly reduce rest bus of modeling efforts. The second effect that we want to see actually, or that we expect to see, is when you kind of sketch how you want to deploy your real-time testing, right? Adding virtual ECUs could change let's say the test path or the test deployment that you will decide for, right? Will it be a single ECU hill? Will it be a multi-ECU hill? Let's say today you typically go for the least amount of real-time systems that you, let's say, need to achieve the best or the needed fidelity of the hardware-in-the-loop simulations. But if you could, let's say, reuse a very validated virtual equivalent of a real-time system, you could say, okay, I have a system under test. This will never go away on a hardware-in-the-loop setup, right? Because that's why we do hardware-in-the-loop testing. But if you could say, okay, I could add maybe, I don't know, 1 or 2 virtual ECUs next to another real one, I could achieve a much cheaper, let's say, system simulation instead of integrating 5 real, let's say a hill which contains 5 real systems. So that's the second area where we expect an impact. Now, let's look at the concept, what we actually want to do. This is a high-level overview. So in the end, we have a simulation running on a PC. It has the software code inside that would usually be deployed on a real-time MCU, for example. And I want to develop that virtual ECU on the left side, validate it, approve it, with respect to model quality, build the trust that we heard in the other talks, let's say, for the simulation, and then in the end, reuse that in the hardware simulation, or the hardware-in-the-loop simulation. Let's look at how this can be possible. We are a bit lucky in that sense because many, let's say most modern hill vendors moved to Linux in the last couple of years, right? So I think when we tried this first and 5 years ago, there were still a couple of QNX around, but by now most of them support Ubuntu. And this is actually quite nice because we as Synopsys, we also support Ubuntu. So that was, let's say, a good architectural change for us to reuse our models. And the other thing where we are quite lucky, let's say, is that also most modern hill vendors, IPG, by the way, also they support FMI, at least 2.0. So we also already have kind of an exchange format defined. This goes into the direction of many other talks today, collaboration and standardization. Because of all the efforts in the last years to collaborate in the industry and build standards together, we actually had a, let's say, reasonably simple time in defining the architecture, right? So we use FMI to integrate the model, and we are lucky with that, with the operating system that runs on the hill. What's the benefit with this design? Let's say, so we get the complete lifecycle management for free through the FMI standard, and we have the option to deploy compiled binaries to the hardware-in-the-loop setup, which is really important if you want to work with many parties, because it's reasonably IP protected. You don't have to share code, and in the end, that's a big requirement for the project that we had. Let's talk about achievements. So. In the end, that was the target, right? We wanted to have, next to the CarMaker vehicle model in the driving simulator, we wanted to have a number of virtual ECUs integrated with the system. And regarding tool development, so that was our part, we were able to, validate that we can build compatible binaries to the real-time simulator of choice. In this case, it was a DSpace Galaxio. We were able to prove that the VECU, build files and all the tool chains for integrating the virtual ECU there were no duplicate efforts, so we could reuse the configurations also for the real-time machine. Actually, the build is the same, so we don't rebuild for the real-time machine. It's just we build for a Linux distribution and validate everything there, and then deploy the FMU to the real-time system. And then this enables all the, let's say, typical collaboration methods. We can share libraries across companies, then build one model from it. That makes it easy to work with third parties. It maintains IP protection. And the big thing is we can shift all the model validation effort to the PC and don't have to, reserve costly real-time system time to actually do the model validation. And on the use case development side, we managed to integrate two ECUs in the real-time simulator. One was quite a big one, an HCP ECU, and one, let's say, a tad smaller, an electrical machine. And both of them have successfully been executed on the real-time system. We also got a couple of learnings because by now it sounded like super easy. You know, the Hill supports Linux. We support Linux. The Hill supports FMI. We do, right? So what did you actually do? So be aware of Linux dependencies. This is quite easy to circumvent, let's say, but be really sure that you pick the correct distribution that matches the Hill environment. And this can be a bit of a, let's say, negotiation efforts when you work with suppliers, because these operating systems need to be approved on both sides. So this is more like a non-technical learning, I would say, mostly. Another big challenge were, you know, actually meeting real-time that was actually not that simple to manage, because in a simulation you can be faster than real time most of the time, and it's not a problem, right? If your setup is running, I don't know, twice real time, you simulate, you're happy, everyone says, okay, this runs above real time. A human says that, but a real time machine can have a different opinion, because let's look at the graph. That was actually the first execution assessment time wise. Every second we didn't meet real-time requirements. And in office simulations, you don't care about that, because you don't even notice if there's a slight variation in simulation speed. But on the real-time system, they really disagree with you on that. So we had a task overrun every 1 second, and in the end, we had to balance the load of the virtual ECU to be actually able to always meet real-time requirements. So that was a bit of, let's say, simulation engineering that is necessary. Also, you need dedicated cores to run the simulation model, but this is typically not a problem, let's say. And another thing that we learned is interface plays a big role, especially when you compare it to, let's say, the step sizes that you want to execute the model in. This is also quite standard, let's say, for a simulation engineer, but you do have to do some engineering. Okay, how fast do I need to execute the model so that I don't pay too much tax for the interface, let's say. So the picture roughly indicates this. If you have a 1 millisecond time step, you pay, let's say, for the interface synchronization every millisecond, and obviously if you execute the model every 2 milliseconds, it might mean that you have to, you know, execute a task that has a 1 millisecond cyclicity twice per step, but you only pay the load for the interface synchronization once. So you have to do you have to check how fast do I need to execute my model and how fast do I need to synchronize the interface. So that's also, let's say, some engineering that you have to invest to actually meet performance criteria. And another thing is, in the end, let's say, a more standard learning, which is, you know, if you integrate a big domain ECU, you might have, you know, a couple of CANs, an Ethernet, and a FlexRay. And FMI 2.0 is signal-based, right? So we map all the networks to signal interfaces, and mapping this and integrating this into a REST bus model is some engineering effort. This needs to be kept in mind. But it's not like so there is still some development to be done there. This can be changed, this can be improved in the future, but this is just let's say the current knowledge, right? Mapping, I don't know, tens of thousands of signals into a REST bus model. You need a good engineering team that does that for you, let's say. Let's talk about the technology outlook. So one thing is parallelization. Right now, this was this was executed in a single thread. So this is in my mind, let's say, a no-brainer. Let's try to parallelize to see how we can more easily meet real-time requirements of virtual systems. We need to review the interface integration. Right now, we are based on FMI 2.0. It's mostly based on doubles. For any just as a review, a double has 8 bytes, and if we were to move that to more exact, let's say, interface types, for example, a single byte interface, you save 8 bytes per signal, let's say, and you can reduce the load of the interface. So this is a technology outlook that we would need to look into. Then again, an argument pro standardization. So FMI 3.0 really invested in interface, let's say complex interface types, and if that would be supported in the hardware simulations and in the virtual ECU simulators, we could move to a new standard. And then another technology outlook is to kind of deploy this to other hardware-in-the-loop systems. As mentioned, we did this on a DSpace in this case, but we've already proven that the binaries can also run on an IPG hill, on a Micronova hill, and actually National Instrument systems. And we are, let's say, working with these 4 vendors to see where we can deploy the solution. And in summary, so what did we do? We proved that it works on a DSpace at Audi, and that we can build FMUs based on existing virtual development build processes, and then just reuse them in the real-time system to enhance the fidelity of those tests. And with that, I would give to Andreas.
Okay. Yeah, I will just finish. Can you hear me? Okay. I will just finish with where we are standing right now. As Franz said, we have successfully integrated one of the central processing units and also one smaller smart actuator VECU. We are still not done integrating the entire control network, which is mainly because we don't get the right binaries. I really want to stress how difficult it is to work with like 2 different tier 1 suppliers and CARIAD and Volkswagen and Audi and Porsche. It's really, that was the hardest part of it. Not the technical problems, but as mentioned today, trust and collaboration were the main problems in this project. Yeah, as I said, our current use case is our own driving simulator, but the goal is, of course, to expand this to the entire hardware-in-the-loop testing, because yeah, the effort, especially for modeling the central processing unit, are really, really high. And if we can change the existing VEC, if we can use the existing VECUs for these big, yeah, main processing units, we could save a lot of money on the hills, and that's what we're trying to do. So we want to integrate on other real-time simulators, and of course we want to get this whole tool chain more efficient, and it's now in the prototype stadium, and of course we have to do the industrialization together with the colleagues from Synopsys. So thank you very much for your interest in our talk, and I hope that we can answer your questions if you should have any.